Welcome! In this session, we'll explore a fascinating problem titled Delete Columns to Make Sorted. This problem challenges us to identify and count the number of columns in a matrix that aren't sorted lexicographically. It's a great exercise in understanding string manipulation and matrix traversal. Let's dive in. In this problem, you're given an array of strings, where all the strings have the same length. Each column in the array is formed by taking the characters at the same index from each string. For example, the first column consists of the first characters of all the strings, the second column consists of their second characters, and so on. A column is considered sorted if, when you look at the characters in that column from top to bottom, they are in non-decreasing order. This means that each character in the column must be less than or equal to the character below it. Your task is to determine the minimum number of columns that need to be removed so that all the remaining columns are sorted. When you delete a column, you remove all the characters in that column from every string in the array. Let's look at an example to understand this better. Suppose the input is an array of strings, CBA, DAF, GHI. Here, there are three columns. Column 0 contains the characters C, D, G, which are in non-decreasing order. So, column 0 is sorted. Column 1 contains B, A, H, where B is greater than A, so this column is not sorted. Column 2 contains A, F, I, which are in order, so column 2 is sorted. Since column 1 is the only one that's not sorted, we have to delete it. After deleting column 1, the remaining columns are sorted, and the minimum number of columns to delete is 1. In another example, if the input is A, B, C, there is only one column, and it contains A, B, C. These characters are in non-decreasing order, so the column is already sorted. Since no columns need to be deleted, the minimum number of columns to delete is 0. Now, consider the input, ZYX, WVU, TSR. Here, there are three columns. Column 0 contains Z, W, T, which is not sorted because Z is greater than W. Similarly, column 1 contains Y, V, S, which is also not sorted, and column 2 contains X, U, R, which is not sorted either. None of the columns are sorted, so all three columns need to be deleted. The minimum number of columns to delete is 3. To summarize, in the first example, we deleted one column to make the remaining columns sorted. In the second example, no columns needed to be deleted. In the third example, all columns were unsorted, so we had to delete all three columns. This demonstrates that the minimum number of columns to delete depends on the arrangement of characters in each column. Finally, let's look at the constraints for this problem. The input array will have between 1 and 100 strings, and each string will have a length between 1 and 100. All characters in the strings are lowercase English letters. There are a few special cases to consider. If there's only one string in the array, then all columns are automatically sorted because there are no other rows to compare with. Similarly, if each string is just one character long, there is only one column, and it is sorted by default. If all the strings in the array are identical, then all columns are sorted as well. Finally, in the worst case, if none of the columns are sorted, the output will simply be the total number of columns, since all of them must be deleted. These edge cases help us better understand the problem and account for scenarios that might not be immediately obvious. To solve the problem of counting columns that are not sorted lexicographically, let's first consider a brute force approach. The intuition here is straightforward. We iterate through each column of the given array of strings and compare characters row by row. If we find that a column is not sorted, we increment a counter. Specifically, for each column index, we loop through all rows and compare each character with the one in the next row. If a character is greater than the one below it, we mark that column as unsorted and increase our count. The time complexity of this method is O, n asterisk m, where n is the number of strings and m is the length of each string, because we examine each character individually. The space complexity is O(1), as no additional data structures are required. While this approach is simple and effective, it may not be ideal for larger datasets, as it involves iterating through every character with nested loops. However, it provides a clear foundation for understanding the problem and its constraints. We can simplify the brute force approach further by using Python's zip function. This allows us to access columns as tuples directly, eliminating the need for manual indexing. Here's how it works. By applying zip **strs, we effectively transpose the grid of strings, so each column becomes a tuple that can be iterated over. For each column tuple, we compare it to its sorted version. If the column is not already sorted, we increment our unsorted column counter. This approach retains the same time complexity of O and **m, since we still examine each character once, and the space complexity remains O1, as we only use a counter. The advantage of this method lies in its simplicity and readability. By avoiding manual indexing, we reduce the likelihood of errors and make the code easier to understand and maintain. The functionality is identical to the brute force solution, but the implementation is far more elegant. The strategy we've chosen combines the brute force approach with the use of zip 4-column traversal. This decision is based on 3 key factors. First, it directly solves the problem in the simplest way possible. Second, the time complexity of O and **m is already optimal, as we cannot avoid inspecting all characters due to the problem constraints. And third, the use of zip makes the implementation concise and minimizes the risk of indexing errors. A key observation here is that each column can be treated independently. Whether or not one column is sorted does not impact the sorting status of other columns. This independence simplifies the logic significantly. The aha moment in this solution comes from recognizing that zip **SRS allows us to handle columns directly without needing nested loops, which greatly streamlines the process. Given the constraints of the problem, there aren't meaningful alternatives to this approach, and the zip-based implementation stands out for its clarity and efficiency. This problem highlights the effectiveness of straightforward solutions when further optimization isn't feasible. By leveraging the zip function, we achieve a balance between clarity and efficiency, creating an approach that is both easy to implement and optimal for the given constraints. The chosen strategy demonstrates how small insights, like using zip to simplify column traversal, can lead to cleaner and more readable code. Ultimately, this solution serves as a great example of how understanding the problem's requirements and working within its constraints can lead to an elegant and effective implementation. To solve this problem, we need to figure out how many columns in a given list of strings are not sorted in lexicographical order. Think of each string as a row in a table, and the characters at the same index across all rows form a column. Our task is to check each column and count how many of them are unsorted. First, we start with input validation. We need to ensure the input strs is not empty and that all strings within the list are of the same length. This is crucial because the problem assumes a rectangular grid structure. If the strings vary in length, the process cannot continue. Next, we initialize 2 key variables. The first is number_columns, which represents the total number of columns in the table, calculated as the length of the first string. The second is unsorted_count, a counter initialized to 0, which will be used to track the number of columns that are not sorted. These initial steps set the foundation for the algorithm to process the data effectively. Now, we move on to processing each column to determine if it is sorted. To do this, we use a loop that iterates over each column index, from 0 to number_columns 1. For each column, we need to compare the characters in consecutive rows to check if they are in non-decreasing order. We begin by setting a flag as _sorted to true, which assumes the column is sorted until proven otherwise. Then, we use an inner loop to go through the rows of strs. For any 2 consecutive rows, we compare the characters at the current column index. If we find that the character in the current row is greater than the character in the next row, this means the column is unsorted. In this case, we set is_sorted to false and break out of the inner loop, as further checks for this column are unnecessary. After completing the checks for a column, if is_sorted is false, we increment the unsorted_count by 1. Once all columns are processed, we return the value of unsorted_count as the result, which represents the total number of unsorted columns. The approach we use to solve this problem is both systematic and efficient, focusing on one column at a time. This column-by-column processing ensures that we handle the data in a structured way and avoid mixing information between columns. The key operation here is the lexicographical order check, which involves comparing characters in consecutive rows for each column. By checking if the character in the current row is greater than the character in the next row, we can determine whether the column is sorted. Additionally, the algorithm is optimized with an early termination mechanism for columns. As soon as a column is determined to be unsorted, we stop further checks for that column, which saves time. In terms of data structures, the input itself, a list of strings, is naturally suited for columnar processing using indices. The unsorted underscore count variable is used to keep track of the result, while the is_sorted flag temporarily holds the state of each column as we process it. This combination of systematic processing and optimization makes the algorithm both simple and effective. Analyzing the algorithm's complexity, we start with the time complexity. The outer loop runs once for each column, so its iterations are proportional to the number of columns, denoted as m. The inner loop checks each row for a given column, iterating n times, where n is the number of rows. This results in an overall time complexity of O(m*n), which is efficient given the problem's constraints. For space complexity, the algorithm uses constant space. Variables like unsorted underscore count and is_sorted take up fixed space regardless of the input size, so the space complexity is O(1). Let's illustrate this with an example. Suppose the input is strs equals cba, daf, ghi. Here, we have three columns. Column 0 contains C, D, G, which is sorted. Column 1 contains B, A, H, which is unsorted. Column 2 contains A, F, I, which is sorted. Since only column 1 is unsorted, the output is 1. This example demonstrates the steps of the algorithm and how the result is computed. To further optimize this algorithm, we can use two key strategies. First, we leverage early breaks. As soon as we detect that a column is unsorted, we stop comparing any further rows for that column. This avoids unnecessary computations and improves performance, especially for larger datasets. Second, we could implement batch processing if the environment supports parallelism. For instance, using multi-threading, we could process multiple columns simultaneously. This would reduce execution time in practice, particularly when dealing with a large number of columns. While the algorithm is already efficient for typical inputs, these optimizations can make it even faster and more scalable for larger datasets or real-world applications where performance is critical. This Python implementation addresses LeetCode problem number 944, delete columns to make sorted, by identifying the number of columns that are not sorted lexicographically. The function min_deletion_size takes a list of strings, strs, as input, where each string represents a row in a table. The goal is to count how many columns need to be deleted to ensure all remaining columns are sorted. ###detailed explanation. 1. Initialization. We initialize a variable delete_count to 0 to keep track of the number of columns that need to be deleted. 2. Column iteration. Using a for loop, we iterate through each column index in the table. The number of columns is determined by the length of the first string in strs, i.e., len, strs, 0. 3. Row iteration. For each column, we check if the characters in that column are sorted lexicographically. This is achieved by iterating through the rows using another for loop, starting from the second row, index 1. We compare the current character, strs, row, call, with the character in the row above, strs, row 1, call. 4. Column validation. If we find a character that is less than the one above it, the column is not sorted. In this case, we increment delete_count by 1 and use break to stop checking further rows in the current column, as it has already been deemed unsorted. 5. Result. After checking all columns, the function returns delete_count, which represents the number of columns that need to be deleted. ###complexity. Time complexity. The algorithm runs in O(n*)m, where n is the number of rows and m is the number of columns. This is because we iterate through all columns and, for each column, we potentially check all rows. Space complexity. The space complexity is O(1), as no additional data structures are used. This concise and efficient approach ensures correctness while handling edge cases, such as when strs contains only one row or when all columns are already sorted. This is the Java implementation of LeetCode problem number 944, delete columns to make sorted. The logic is equivalent to the provided Python solution but adapted to Java syntax. Key differences include the use of Java's char for string indexing, explicit type declarations, and standard Java class structure. The method iterates through columns of the given array of strings, checking if each column is sorted. If a column is unsorted, it increments the deletion counter. The final count of columns to delete is returned. In the first example, we are given the input array of strings strs equals cba, daf, ghi. To determine the number of columns that need to be deleted to ensure all columns are sorted, we initialize delete_count to 0, which will track the number of columns marked for deletion. Since each string in the array has the same length, the number of columns is equal to the length of any string, which in this case is 3. Starting with column 0, we observe the characters C, D, and G from top to bottom. Comparing adjacent characters, D is greater than or equal to C, and G is greater than or equal to D, so column 0 is sorted, and no deletion is necessary. Moving to column 1, with characters B, A, and H, we notice that it is less than B, meaning column 1 is unsorted. As a result, we increment delete_count to 1 and stop further comparisons in this column. Examining column 2 in the same example, we have the characters A, F, and I. Comparing them row by row, F is greater than or equal to A, and I is greater than or equal to F, indicating that column 2 is sorted. Thus, no deletion is required for this column, and delete_count remains 1. At the end of this example, the total number of columns that need to be deleted is 1. Now, in the second example, the input is strs equals zyx, wvu, tsr. Here, we again initialize delete_count to 0, and the number of columns remains 3. Let's analyze the columns one by one to determine which ones are unsorted. Looking at column 0, which contains the characters Z, W, and T, we compare W with Z and find that W is less than Z. This indicates that column 0 is unsorted, so we increment delete_count to 1 and stop further comparisons for this column. Next, examining column 1 with characters Y, V, and S, we observe that V is less than Y, which means column 1 is also unsorted. We increment delete_count to 2 and move on. Finally, for column 2, the characters are X, U, and R. Comparing U with X, we find that U is less than X, so column 2 is unsorted as well. We increment delete_count to 3. At the end of this example, all columns are unsorted, and the total delete_count is 3. In the third example, the input is strs equals abc, bcd, cde. Again, we initialize delete_count to 0, and the number of columns is 3. Starting with column 0, we have the characters A, B, and C. Comparing adjacent characters, B is greater than or equal to A, and C is greater than or equal to B, so column 0 is sorted, and no deletion is needed. Moving to column 1, the characters are B, C, and D. Here, C is greater than or equal to B, and D is greater than or equal to C, indicating that column 1 is also sorted. As a result, no deletion is necessary for this column. Finally, in column 2, we have the characters C, D, and E. Comparing them row by row, D is greater than or equal to C, and E is greater than or equal to D, confirming that column 2 is sorted. Since all columns in this example are sorted, no deletions are required, and delete_count remains 0. The output for this example is therefore 0. This concludes the walkthrough of all 3 examples, illustrating how we determine the number of columns to delete to make the strings sorted column-wise. To analyze the time complexity of the solution, we start by examining the 2 nested loops. The outer loop iterates through each column of the input strings, and if there are m columns, this loop will run m times. Within this outer loop, the inner loop is responsible for comparing adjacent rows within the same column. If there are n strings in total, the inner loop performs up to n1 comparisons for each column. When we combine these 2 loops, the total number of comparisons made by the algorithm is the product of their iterations, resulting in m*n1. In big O notation, we drop constants in lower order terms, so the time complexity simplifies to O, m*n, where m represents the number of columns and n the number of strings. This provides a clear picture of how the runtime scales with the size of the input. Now, turning to the space complexity, the memory usage of the solution is primarily determined by the input. The input strs consists of n strings, each of length m, meaning the input inherently requires O, m*n, space to store. Beyond this, the algorithm only uses a small number of auxiliary variables, such as an integer delete_count to track the count of columns to delete and the loop index variables like call and row. These variables consume constant space, or O1. Importantly, no additional data structures are created during execution, which means the auxiliary space complexity is O1. Overall, the space complexity of the algorithm is dominated by the input storage, which is O(m*n), but the algorithm itself is efficient in terms of auxiliary memory usage. Next, let's evaluate the algorithm in terms of best, average, and worst-case scenarios. In the best case, all columns are already sorted. Here, the inner loop completes its checks without breaking early, resulting in the full (m*n) comparisons, and the time complexity remains O(m*n). In the worst case, where all columns are unsorted, the inner loop exits early for every column after just one comparison. However, the outer loop still iterates over all columns, so the time complexity is still O(m*n). On average, the early termination in the inner loop reduces the number of comparisons per column, but the big O complexity remains O(m*n), since we always consider the worst case for big O analysis. When compared to a brute force approach, which would involve extracting and sorting each column, the current solution is significantly more efficient. A brute force method could have a time complexity of O(m*n log n due to sorting and would also require additional space to store column copies, increasing its space complexity to O(m*n). The current solution avoids these inefficiencies, making it a clear improvement. The optimized solution achieves a time complexity of O(m*n and an auxiliary space complexity of O1. By avoiding unnecessary operations like sorting or copying data, it operates efficiently in both time and space. To mathematically validate the time complexity, the outer loop runs m times, and for each column, the inner loop performs at most n1 iterations. Multiplying these results gives a total of m*n1 iterations, which simplifies to O(m*n when expressed in big O notation. Since constants and lower order terms are irrelevant to big O, this confirms the time complexity. In conclusion, the provided solution is not only efficient but also memory-friendly, outperforming brute force approaches by avoiding redundant computations and additional memory usage. This makes it well-suited for solving the problem at scale. When working on this problem, there are some common mistakes to watch out for. First, many people mistakenly compare rows instead of columns. Remember, the problem is specifically about ensuring that columns are sorted lexicographically. If you iterate row by row, you're missing the vertical ordering requirement, which will lead to an incorrect solution. Next, some solutions stop after identifying just the first unsorted column. This is problematic because the task is to count all unsorted columns, not just the first one. Another common issue is incorrect indexing. When accessing elements like strs, j, I, it's easy to mix up rows and columns. Since j represents rows and I represents columns, any misalignment here can lead to runtime errors or incorrect comparisons. Lastly, edge cases such as empty strings, single-row inputs, or columns with identical characters are often overlooked. Skipping these can cause your program to crash or produce unexpected outputs, so it's important to handle these cases explicitly. Inefficient nesting of loops is another mistake to avoid. For instance, checking every character in every column without using early exits can drastically increase time complexity, especially for larger inputs. Instead, aim to optimize your loops to reduce unnecessary work. Speaking of optimization, here are some key interview insights. First, always ensure you fully understand the problem scope. It's about column-wise comparisons, not row-wise. Misinterpreting this can derail your entire approach. Additionally, while optimizing for efficiency, remember that once you know a column is unsorted, there's no need to continue checking further down that column. Another critical aspect is edge case thinking. Make sure your solution properly handles inputs like empty arrays, matrices with only one row, or columns with duplicate characters. Lastly, during interviews, clarify input constraints with your interviewer. For example, ask about the maximum size of rows and columns or whether the character set is strictly lowercase letters. This can help you tailor your solution appropriately. Now that we've covered common pitfalls and tips, let's look at some related problems that can help reinforce your understanding. The most directly related problem is LeetCode 944, which is the one we're working on, counting unsorted columns in a matrix. Another interesting problem is LeetCode 953, where you verify the order of words according to a custom alien dictionary. It's a twist on lexicographical order but involves a different alphabet. Then there's LeetCode 937, where you reorder log files based on lexicographical sorting of their contents. While not directly about columns, it shares the concept of sorting based on specific rules. Finally, LeetCode 791 involves custom sorting of strings based on a given order. These problems all revolve around sorting and ordering, making them excellent practice for sharpening your understanding of lexicographical rules and array manipulation. Let's discuss alternative approaches and their trade-offs. The brute force approach involves directly comparing each character in a column to the one below it. While this is straightforward to implement, its time complexity is O, n asterisk m, where n is the number of rows and m is the number of columns, making it inefficient for large inputs. A more optimized approach is to use early exits. If you detect that a column is unsorted, you can stop further checks for that column. This can reduce the time complexity to O, n, in the best case, though the worst case remains O, n asterisk m. While this method is slightly more complex to implement, it's more efficient overall. Another less common approach is matrix preprocessing, where you transpose the matrix to simplify column-based checks. This involves preprocessing time of O, n asterisk m, followed by the regular checks, and might introduce unnecessary overhead for smaller matrices. Choosing the right approach depends on input size and efficiency requirements, so weigh these trade-offs carefully. Great job! We've successfully tackled the delete columns to make sorted problem. Remember, understanding the fundamentals of lexicographical order and practicing matrix traversal is key. Keep challenging yourself with similar problems, and don't forget to like, share, and subscribe. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!